In this video, I'm going to introduce you to some ideas related to colorimetry. Now, colorimetry is sort of what it looks like if you look at that word. Colorimetry is sort of measuring or metry numerically and studying numerically the color of something. And in this case, we're talking about the color of a solution. So colorimetry is sort of a numerical way of studying the intensity of the color in a solution. So colorimetry involves solutions that have a color. And so in this packet, hopefully you have one like this, or in these problems, you'll see solutions that have a color. And so right off the bat, in this first question, a little further down the page here, it says we have an emerald green solution. Colorimetry is very difficult to do if you're talking about a solution that has no color, like salt water or a sugar solution. There's really no visible color that we can look at and identify with our naked eye, and it's difficult most of the time for a typical colorimeter to measure the intensity of a color in a solution that doesn't have a color that we can see with our eyes. So typically when we talk about colorimetry, we'll be talking about solutions that have a color, visible color, whether it be any one of the colors of the rainbow, in this case emerald green. Different solutions of various metals have a color that's sort of related or certainly common to them. And so in this case, nickel is our metal. Nickel has a color that's almost always some kind of pretty cool green, for example. Coppers tend to be blue, for example. As we look at others, you'll see some other colors that come along as well. So typically the color of a solution, when we're talking about salts like nickel chloride, are related to the chemistry of the metal. And it almost always has to do with a transition metal somewhere in the middle of our periodic table, and the valence electrons of that metal and how light interacts with it and all that business. I won't get into all that because I'm not qualified, I would say, to explain to you exactly why the colors are what they are. But the colored solutions that we observe are, in terms of salts like these, are typically related to a transition metal like nickel, copper, iron, lead, some of these sorts of metals. And so as we look at the problems, you'll notice there's a kind of a repeating pattern of color related to those metals as well. Now, in this packet, you've got a link here at the top. It's going to take you to a Phet simulation. A Phet simulation here is a series of simulations that are online, organized through a group in Colorado, and they're really, really good. They're cool and interactive, and we can simulate some things rather quickly and efficiently to collect a lot of data in a way that would make it time-consuming in the lab or impossible, because often we just don't have the equipment, or because the simulator is doing something that isn't very possible at our macro scale. It's showing us something perhaps involving molecules or atoms, which obviously we can't go in the lab and manipulate. So in our first simulation here, this Phet Simulator, you can type this address in. Here it's the shortcut for it. You could always just search Phet Simulator on Google or some other search engine and find Phet simulations out there on the internet. They're very easy to find. The Phet simulations are really good and quite popular. You'll see me refer to a few as we go throughout the year. Okay, so the Phet simulation, if you go to that link, will actually take you to a page that looks like this, and it takes you to a title, Beer's Law Lab. Beer's Law, or the Beer-Lambert Law, named after a fellow by the name of August Beer, and he is a German who lived in the early to mid 1800s, died right around the time of the American Civil War, and was a guy who invented something called the photometer. And a photometer is the device that we're going to use in this simulation of Beer's Law on this website, again from Colorado, through the Phet simulations. And we're going to use the Beer's Law one, so you want to be on this Beer's Law side if you go to that address. And if you click on that a time or two, it'll take you to this screen. Hopefully, you'll find this without a whole lot of trouble. And then we'll start manipulating some of the factors that are on this page. Okay, so we'll come back there in just a second. Now, a Phet simulation, in this case, is going to talk about colorimetry, assuming you've got a little bit of understanding. And it may be the case that you don't. So I'm going to take you through just a quick kind of crash course on what colorimetry is about. Then we're going to come back to this and gather some data. So studying solutions with a colorimeter, again, allows us to measure the intensity of a solution and then use that to our benefit to identify what's in it, or perhaps how much of something is in the solution. Colorimetry here, it says, concentration of a solution can be studied using colorimetry if the solute has a color. So in the picture here, you see all kinds of colors, from a clear solution on the left here, all the way through the many colors of the rainbow and different intensities of some of those colors as well. The idea is that the darker or more intense the solution is, the more of the solute must be dissolved into it. Now, we don't work with metal salt solutions very often in our everyday lives. So imagine in these little tubes, they're called cuvettes, and you'll use these in lab as well. Imagine that these little tubes are containing small samples of, say, Kool-Aid solutions. You can imagine that if you were mixing up a Kool-Aid solution in a cup or in a pitcher, that the more Kool-Aid powder you put into the pitcher, the more dark the color would appear, the more intense the color of that solution would appear. If you put just a small amount of Kool-Aid into a whole pitcher of water, the color would be very pale. If you dumped in more, it would intensely get more and more colored, and the darker it got, we would assume, the more you had added to that pitcher. Well, the same thing applies to us as it applies here in chemistry to how much solute, which is simply the part that's dissolved into a solution. So how much solute you've added to the solvent. Usually we're talking about water as our solvent. So in this case, the more solute you've added, the darker the color will get, the more intense the color will get. That only works, again, if the particular salt gives a color at all. So if you put a little salt into water, it looks clear, like water. If you put a lot of salt into water, it looks clear like water. So things like table salt, sodium chloride, they don't have a visible color. It might be the first tube you see here on the left, as opposed to things like copper sulfate or iron chloride, where they have a color that's quite visible, and some of the others that you'll see here as well. So colorimetry, it says in the last bullet, usually works best with colors visible to our eyes. So here's the basic idea of colorimetry. As we're studying it, we need to first choose a color that's most appropriate to study the solution that we're interested in. So as we go to the first questions in this packet, you're going to find in each case the color that we choose will be different. What we need to do is choose a color that's complementary to the solution's visible color. So if I had an orange solution, it's orange not because it's giving off orange light, right? Something looks orange in a glass, like a glass, say, of Tang or orange Kool-Aid or something. It doesn't look orange because it's giving off orange light. And we know that because if I shut the light off, it doesn't look orange anymore. It looks like nothing. We can't see it. If it continued to glow while in the dark, then it is emitting its own light, and that's a whole different story. But here we're talking about a solution that looks orange when you shine light on it. And the reason it looks orange is because the orange light that you're shining on it is the light that's passing through it. If I shine light from a typical light bulb onto a glass containing an orange Kool-Aid or other orange solution, it looks orange because the orange light is passing through the solution and the other colors are being absorbed or taken out of the solution. In the picture that you see here, the colors are being shown through, all these colors are being shined through this, what looks like in the middle there, a green tube of solution. And you can tell that some of the colors are getting through a little bit, like the purple and the red. Some of the colors aren't getting through much, but then there's the green light that's getting through basically completely. And that's because the green light is being transmitted through the green solution. The other colors that are least light green are being absorbed by the solution. Now, if you're into art, you might know about complementary colors. And here's some stuff with like basic color wheels, primary colors, and that sort of thing. So if I was to study, like we saw in the previous example here, a green solution, I can see in the very top left sort of color wheel here that across from green in our color wheel is red. And so if I was to study a green solution, I would want to use a red light. Reason being, a green solution will most effectively absorb a color that complements its visible color, the color that's least like it and directly across from it on the color wheel. So if I'm to study a green solution, I want to use a red light, not a green light. And the reason for that, again, is because as I add more of the green solute, and our first example on the sheet there says nickel chloride is green, so we're going to use red for that. The reason is the more nickel chloride is in the solution, the more of that red light it will absorb. The greener the solution is, the more red light it will absorb. And so as I vary or change the amount of nickel chloride in my solution, the amount of light being absorbed will increase with that. And I can measure then how much nickel chloride is in it by measuring how much red light has passed through. Now hopefully that makes sense, but think about this color wheel as you start choosing colors, complementary colors for you in various solution situations. And you don't need to memorize this color wheel because frankly, most of us know the colors of the rainbow. We learned about Roy G. Biv somewhere in our life. Red, orange, yellow, green, blue, indigo, which is sort of debatable, they tell me, and violet. Those colors of the rainbow. Now, blue and indigo are basically related or pretty similar. So we're going to leave indigo out for our purposes, and we're just going to talk about 6 because, it makes it easier for me to draw it, if we're being real honest. So what I'm going to do is take those 6 colors, and instead of just writing them in a line, just write them in sort of a crude circle. So Roy G. something like that, sort of like a clock. And that way, if I'm studying a green solution, here, I just look across to the red, and that's the color I would want to use to analyze my green solution. Right? If I was using, say, a blue solution, or let's say an orange solution, if I was going to study an orange solution, I would want to look across the way and choose a blue light to study that orange solution. And if I was using a violet solution, I might pick a yellow light to do that, to study it. So across the wheel is the color that you'd want to choose to study a solution of a particular color. All right. Now, we can use a device called a spectrophotometer, which sounds very fancy, and is a sort of updated version, I suppose, of what Beer invented. And it actually shines through a solution all the colors of the rainbow, and it helps us to decide which color is most appropriate. So here's a kind of an output picture from what would be a spectrophotometer, one like we have in class called a SpectroVis. Now what it does is it shines all these colors of the rainbow through a solution, and it shows us how much of that particular light is being absorbed by the solution that we're studying. So I stick a sample in my spectrophotometer, and out comes this information. That red kind of curve you see through the middle obviously is very high over in the purple and blue wavelengths. It's very low on the far right side over on the reddish wavelengths, and kind of in the middle there's some variations in height. But what you want to do is look for the place where the color is the highest. Right? So as I choose my color here, if I was to pick a color to study this solution, I'd want to choose the one that's the highest here. The purple would be my color of choice because it has the highest absorption. This is probably data from a yellow solution. So if I put a sample in, I'd pick the peak, look for the highest point, and pick that color to help me study the solution. Okay. Now, as we look at the problems that are in your packet, we're going to use that idea to help us choose it without even having to look at data like this. We're going to look at the data or the color wheel and choose our color from there. Now, the final piece is this. What determines then, what about a solution determines how much light is absorbed? In colorimetry, a different amount of light will be absorbed based on several factors. And here's kind of a quick drawing of what's happening inside of our colorimeter or inside of a spectrophotometer. What it's doing is shining a light source, which you see there on the left side, through a collimator, which basically lines up the wavelengths or the beams of light and puts them in a certain line, shines it through a prism to scatter that light into the rainbow. And then at various intervals, the different colors are passed through what you see here in the middle as a slit. Right now, the yellow light in this picture is being allowed to pass through the slit. In other words, it's selecting the yellow wavelengths. So you see it there labeled as a wavelength selector. And then as that yellow light passes through the solution, some of the light passes through, some of it might be absorbed, and out the other side, some of the light is detected by the detector or a photocell. It measures how much intensity there is in that yellow light coming through, and it outputs it on the display, which you see there on the far right of the picture. What kind of data is that? This would typically then be for us, pardon me, I didn't want to use a white there. This would probably be what we call absorbance data. Absorbance tells us how much of the light is being absorbed. Now, it's not as simple as like 45% in this example. There's a little bit more math to it than that. But 0 would mean that none of the light is being absorbed. And the highest value on the absorbance meter is 2. So the scale goes from 0 to 2. 0 meaning none of the light is being absorbed. 2 meaning basically all of that light wavelength is being absorbed. We don't ever really get to 2, and we rarely see 0 unless we're looking at a clear solution or like distilled water or something. So somewhere between 0 and 2 is our absorbance range, and that's the range that you'll see as well. Okay, from no absorbance to some absorbance. All right. So as we go through our information here, as we go through our data, and you look at the numbers that you're collecting, you'll see that absorbance ranges anywhere from 0 to 2. Okay. Now, keep this in mind as we go through our data and we simulate, because the spectrophotometer or the colorimeter rather that's shown there on the Phet simulating page is actually pretty good. It isn't quite this complex, but it allows us to look at the same sort of information for colors that we select and for solutions that we select. So one of the factors that will determine then how much light gets through is, as we've talked about, the concentration of the solution. So that's one. Okay. How much of the solute is in there? So the concentration of our solution, or the solute dissolved in the solution. That's the first and probably the most obvious factor. If I put more Kool-Aid or salt in our problems here, a particular metal salt, into a solution in water, the more I put in, the more of the light will be absorbed by that solution. So the concentration matters a great deal. The second factor that actually matters a lot as well is how thick of a tube you're using there. And you see it labeled here as the cuvette, right? Here's our cuvette. How wide is the cuvette? So the width of the cuvette is kind of a big deal. Width of the cuvette. If the cuvette is skinny, then the light doesn't pass through very much of the solution, and not very much light would be absorbed. If the cuvette is wide, then obviously the light is passing through more of that solution, and more of the light will be absorbed. So we have to know the width of the cuvette, and we call that the path length. In other words, how long is the light's path through the solution? So path length. Concentration in our problems we'll abbreviate as C. The width of the cuvette we'll measure and actually use and label as B, lowercase b. Absorbance here, as we see it up here, is typically shown as capital A. So absorbance, or how much of that light is being absorbed, and that's what's displayed over here on the display of our colorimeter. So we have absorbance, we have concentration, and we have the path length, or the width of our cuvette. Typically our width of our cuvette's 1 centimeter, but it doesn't always have to be. Now there's one other factor that comes in, and it's sort of an X factor, and actually we abbreviate it not as an X, but as a lowercase a. And it's called the Molar absorptivity constant. Now that's a big fancy word that basically says every salt has its own little sort of factor that makes it absorb or not absorb very effectively, and it's there just sort of to complement the rest of the equation and make the math work out in a way that makes sense and is graphable and useful to us. It's been determined by people way smarter than me over the years, and is a number that you'll need to have in order to do calculations of absorbance. We're not actually going to do those calculations today, so more on the molar absorptivity constant later. But in the end, Beer's law, or the Beer-Lambert law, is A equals A times B times C. And you'll see it a lot of other ways out there on the internet as well. Beer's law, often abbreviated with various Greek variations on those same letters. So it's not always A equals A times B times C. Sometimes you'll see Greek letters in there and some variations on those abbreviations, but those are the ones that we'll stick with. And the A equals A times B times C is actually an equation that's on your constants and formulas page for our class. All right, now I'm not going to go through this whole packet with you, which is good news and bad news. It's good news because this video would be very long if I went through all 4 with you. But it's also good news because after I do just one, I think you're going to know exactly what to do. And I don't want, but the bad news is you won't have me helping you, but the good news is you'll get to try it for yourself and see if you can figure this out. It's really not very difficult. So you're going to be online to do this, and obviously if you're watching this, you're probably online too, and you're going to need to be able to get to this simulator address. You're also going to need to be able to use a spreadsheet of some kind, or if you wanted to just collect data on a piece of paper and then draw it out manually on a graph sheet, you could do that too. It's probably a little bit easier to do it on a graph paper, or rather on a spreadsheet, and generate the graph there. And I want you to try that if at all possible, because in class you're going to have to be able to come up with a standardization curve, as you'll see us make here, and do that on a computer. It's more accurate, it's more appropriate. We'll also eventually show you how to do the same thing on your calculator if you have a graphing calculator and aren't already sure how to do that sort of graphing on there. But for now, I'm going to do it on Google Sheets because most of you probably have access to that. So start a blank Google Sheet eventually. If you want to pause me and get a blank Google Sheet open, you can do that now too. I'll start with a fairly blank one here in a minute, and you can kind of model yours after me. So let's get started here with some data. Now, it says here in the first question, you're going to analyze a solution of nickel chloride, which is emerald green. Which color of light would you recommend to be used to study the nickel chloride solution? Well, remember, in our Roy G. Biv color wheel, across from green was red. So we're going to use red. And again, the reason is red complements green, and green solutions will absorb red light very effectively because it's the least like green. And that's not a very good optics and physics description. It's the least like green, but it's good enough for us here. It's the most complementary color. And again, if you're into art, you might know complementary colors quite well. Now, in the Phet Simulator, it says here, set your light source to a wavelength with the color you chose above. So we want to choose a wavelength that's red. So I'm going to flip over to that simulator here, and we're going to choose a red wavelength, but we also need to choose nickel chloride first. So it doesn't really say that in the instructions. Let's make sure we're looking at nickel chloride. So here on this little pull-up arrow, you have choices. Drink mix, like Kool-Aid. They can't call it Kool-Aid, I suppose, or they get sued. But down here is nickel chloride, nickel 2 chloride. That's the one we're studying. Notice how it's green. You'll also notice that on our device here, it's not turned on right now. So let's turn it on, and that's this fancy little red button here. And as soon as you turn it on, boop, it starts shining out what looks to be like kind of a bluish light here. Now, we're going to choose a color to shine through. Okay, this green tube you see here in the middle, which is our cuvette. And we want to measure absorbance. So up here in the top right corner of your screen, let's make sure we choose absorbance. Now, remember the instruction that we're following here is set your light source to a wavelength with the color that you chose above. And that was red. So we want to choose a red wavelength. And if you're not sure what that is, go here to variable. Let's choose variable, put it on variable. And then you can pull this slider across any colors that you want. You'll notice that that beam of light coming out of the light source on the left changes along with your slider. And we want to choose apparently a red color. Okay. Right, so why a red color? We want a very high absorbance. We want to get a very high absorbance. So I'm going to choose a red color because a red color should absorb fairly well in a green solution. Oh shoot, I refreshed. My apologies. Let's try this one more time. All right, let's turn this on and put our red light up here. Oh, and we want to put a nickel chloride, sorry. And we want to be on absorbance. All right, one more time. Get it back here to a red light. This is not behaving properly. What's going on? It should be a higher number in our red wavelengths, but this simulator is not behaving the way I would expect it to right now, and I'm not sure why that is. It's a little bit weird. I'm being real honest with you. We're not getting the numbers we'd expect necessarily in the red wavelengths here. But we're going to stick with our guns here and set it over here in a red wavelength that gives us the highest absorbance possible, which is it's showing up here at about a 0.22. Okay. This is a deep red wavelength. I'm not sure why it's not a higher one. But pick a red wavelength over here. I'm going to put it there at about 728 nanometers. Okay. The human eye has a visible range that's not very wide in the overall electromagnetic spectrum, and 728's kind of on the long end of that wavelength range that's actually visible. So this is moving toward the end of our red color range that we can actually see. Now, let's go back here to our spreadsheet, and it says record the wavelength that you used. So I'm choosing 728 nanometers. You don't need to choose that. You can choose any wavelength you like, but you should probably be in that red range a bit. If you chose a different color, just make sure you write down the wavelength that you picked. So 728 is the number I'm going to work with. You feel free to use your own number, whether it's there real close to that or even something on a different part of the spectrum, but you want a higher absorbance number. Now, notice here it says you've prepared solutions of various molarities. So this is hypothetical. We've prepared these in the lab. Test each with the colorimeter to measure the absorbance for each sample and record your data in the table to the right. Now, you'll notice this has 5 samples in it. So we have 5 samples, 1, 2, 3, 4, 5 samples. And typically when we're doing what's called a standard curve or a standardization curve, we want at least 4, maybe 5 different points or different samples to test. The more points you get, the more statistically valid it will be. So we're going to test solutions with concentration or molarity here, which is moles in a liter of solution, of 25, 75, 125, 250, and 400. So kind of a range of various concentrations from fairly weak 25 up to much, much stronger 400. And then we're going to record the absorbances that are the result when we put those concentrations on a colorimeter. So my first one here is 25, and let's go check that out. So go over here to my simulator, and we want to set the concentration to 25. That's down here at the bottom of the screen. Notice it says concentration is set at 100 right now. We want to pull the slider down to 25. So slide it down there, and it'll give you a corresponding absorbance value up here on the display. So for 25, I'm getting an absorbance of 0.05. Now I'm going to read my numbers off as I go. I'm going to record my numbers in my table. You do the same with your own numbers, even if they're not the same as mine. Okay? You want your own data. So I've got an absorbance of 0.05. The next molarity on our list is 75. So we're going to switch this and slide this slider to 75. There we go. And that gives me an absorbance of 0.15, 0.15. So I'm going to record that as well. Now I will say one thing about the Phet simulators is they're mathematically, the data is just like nice and perfect. And that's not good in every sense because it gets us a little bit spoiled in thinking it's always going to be so perfectly predictable, and it's not. When we get in the lab and actually do our own standard curve, the first lab of the year is the one I have planned for this, you'll find out the data is not always this perfect, but it probably works about as well. So next number, 125. Let's slide that slider to 125 and measure an absorbance of 0.25, all right? 0.25. Again, hopefully you're writing down your own numbers. If you used a different wavelength, you're probably getting different numbers. The next one is 250. So I'm going to slide my slider to 250. And my absorbance shows up as 0.50. Again, if you're kind of recognizing these patterns, it's kind of unfortunate how perfect these numbers come out because it makes our graph look too good to be true, because it is. But it's a simulator, so sometimes things aren't very varied when they should be. The last one is 400. So let's go back to our simulator once more and set it to 400. Uh-oh, it maxed out at 350. So we can't even get to 400. What then? It's okay. Let's write down our biggest number or really any other number in between. So my last one was at 250. Just because I don't like all these nice numbers, I'm going to put this at some random number, like 316. You can choose your own random number. Just make it bigger than the last one. And so I'm going to be at 316. Let's update our data table so we don't have the wrong number in there. I'm going to use 316. And my absorbance there was 0.63. All right. So now we've got enough data points here to go ahead and make our Google Sheet. So if you haven't already opened a Google Sheet, go ahead and do that, blank one. I've already got one opened up. And I titled it Colorimetry Practice Problems. You can title it rather, something like that. And I've actually set it up in advance, so I have the columns ready to go. So if you want to take a minute to have the same headings and sort of things as I have here, go ahead and pause me for a minute, keep this on the screen, make yourself a little table like this in a Google Sheet, and then unpause and we'll get back to business when you're ready. Okay, so pause me if you need to and get your table ready, and I'll be here when you're ready. Okay, so hopefully you set up your table to look something like this, and we're going to go ahead and put our data from our written down data into this table. You could, of course, make this table from the very beginning and record your data in here immediately. We just did it on paper to start with. So I have values for my molarity of 25, 75. I'm going to go ahead and put those numbers in my table. 25, 75, 125, 250, and 316. All right. It doesn't even matter if you go in order. These could be all over the place, smallest to largest or any mixed match that you want, as long as you keep the molarity and its corresponding absorbance matched up. Okay. So our second column here, or our last column in the table, was absorbance. In my little table here, you'll see it labeled ABS. That's kind of a typical way of abbreviating absorbance. So if you see ABS, that's probably what it's talking about. Unless it's a light on the dash of your car, then it's your anti-lock brake system. You should get that serviced by a professional. Molarity, though, 25, the absorbance was 0.05. All right, and then my second one was 0.15. My next one was 0.25. And if I'm going too fast, of course, feel free to pause and do your own thing here. At 250, I got an absorbance of 0.50. And then at 316, I got an absorbance of 0.63. So there's the data from my data table popped into an Excel sheet. All right. That data over here exactly the same. What we're going to do next is make a graph. Now in Google Sheets, at least right now, they call graphs charts. Graphs are better, but it doesn't really matter. We can deal with it. We know what they need. We need a scatter plot graph or scatter plot chart. So it says here then insert a graph, again called a chart in Google Sheets. So to do that, you can go insert and choose chart. There it is. There's also the chart button, which is over here on your toolbar. Either way will get you the same thing. Now before we do that, we can actually help Google Sheets out a little bit. We'll say, which data do you want to have in your graph or your chart? Well, I want it to be these two columns. I want molarity and I want absorbance to be in there. So you can highlight those two sets of data, the molarity and absorbance, and then go ahead and click Insert Chart. And it'll make one from that data, lickety-split. Okay. Now the first thing that might pop up here is a bar chart, or they call it a column chart. We don't want a bar chart. Bar charts aren't good unless you're studying like a population growth or something like that. Let's change this to a scatter plot. So if you've got a chart that's up like this, and again, all I did was choose my Insert Chart button up here on the top of my screen. And then as soon as it generated the chart, it gave me my little chart editor bar on the side over here. I want to make this a scatter plot though. So I'm going to choose this, and I'm going to go down a little ways here until I see the dots under scatter. And I'm going to choose that. Now it's going to turn those bars into just points that are plotted on an XY kind of graph. All right. It's got my graph. It's got my chart. Let's go ahead and see if we can get a best fit line plotted in here too. Now you can see across the X on the bottom that it's got the values of 50, 100, 150. So obviously that's my molarity data from my data up above. And then on the y-axis, it goes from 0 up to 0.2, 0.4, 0.6, 0.8. And if you roll over here, it'll tell you that this point represents 316 and an absorbance of 0.63. So in my chart here, molarity is on the x-axis and absorbance is on the y-axis. That might be helpful later on. So I might jot that down or add it to your table. On our chart though, okay, and if you lose your little editor bar over here, just double click your chart and it'll bring your editor bar back up. Okay. Now, the next thing we want to do here is on our chart, add a best fit line. And again, Google Sheets has a different name. They call it trend line. So we want to add a trend line to it. A couple ways you can do that. Click out here in your data, on your points. If you click any one of those points, it'll start to highlight it over here on the side. And under the tab or the expandable menu here of series, you'll see this option for a trend line. So I'm going to choose that. Let's add a trend line. And what it'll do is draw in that best fit line for you. And you customize the colors and all that business. Not important that we do all that, but it is important that we label this line. And in the instructions, it says, be sure to show the equation on your graph. The way you do that is you choose the label here as use equation. And what it will do then is in the legend of your graph, it will give you a y equals mx plus b, so a sort of a slope-intercept format. It'll give you the equation for the best fit line that you just added to your graph. And now our graph is more or less ready to go. Now one thing I'm going to do here on mine, just because I like it to be set up so that the axes go from 0 to 0, I'm going to go down here on my x-axis. I'm going to double click on that so that I'm highlighting those values. If yours is like this too. And then I can go over here on my chart editor and tell it I want the minimum to be 0. Okay. So that it goes from 0 up to whatever the maximum might be. And if I see this graph kind of goes off beyond 300, I want a nice round number. Maybe I'm kind of into nice round numbers. I'm going to say, let's make that graph go from 0 to 400. Something like that. You could change the y-axis just the same way. It really doesn't matter much, and it won't affect your equation, but it makes it nice and crisp. It makes it a little bit more exact. Now, it also says record the slope-intercept equation for the best fit line here. Slope-intercept is that y equals mx plus b format. So let's close up, let's go back to our chart here, close up the chart editor, and now we can use that graph that we had drawn. It's got the y equals mx plus b equation. It's right here in the legend. Mine says 1.99 e negative 3. Now hopefully you recognize that as 1.99 times 10 to the negative 3 times x plus 4.45 times 10 to the negative 4. Now it doesn't say y equals, but that's what that represents. Y equals that. So I'm going to write that on my answer, on my sheet there. 1.99 times 10 to the negative 3x. Okay. Let's see. 1.99 times 10 to the negative 3 x. And yours, if you're using data like this, I'm suspecting you got the same equation that I did, because the simulator at Phet is just a little too perfect. And it's okay. But now that's not the whole equation. It says plus 4.45 times 10 to the negative 4. Okay? Plus 4.45 times 10 to the negative 4. Now I'm putting these quantities in parentheses because the whole darn thing is set equal to y. So there's my equation. Y equals 1.99 times 10 to the negative 3 x plus 4.45 times 10 to the negative 4. This, hopefully in your head, resembles a y equals mx plus b format. And there's so many places in science where that slope-intercept graph is actually in play. We use it all the time and we don't even recognize it. But that's y equals mx plus b for this graph. Now it says, using your best fit line equation, calculate the molarity of a nickel chloride solution that has an absorbance of 0.512. Now you look at this and say, what? I don't have any of that information. This isn't anything like absorbance and molarity. What are you talking about? But it is, because look what we did on our graph. Go back one more time to the spreadsheet. Remember what we did? We said molarity is on the x-axis. That means my x value is molarity. So I'm going to write this equation one more time. I'm going to say 1.99 times 10 to the negative 3 times not x, but what x represents. And again, once more, that's molarity. X is on, or rather, molarity is on the x-axis. So whatever I plug in for x should be a molarity value. So I'm going to put that here instead of the letter x. I'm going to put molarity in its place. And then plus b. Okay. And b doesn't change. 4.45 times, 4.45 times 10 to the negative 4. Okay. Now what about y? Y is, according to our chart over here, our data table, y was our absorbance values. So instead of y, I'm going to say absorbance equals 1.99 times 10 to the negative 3, that's the slope of my line, times the molarity, plus the slope of the y-intercept, rather, 4.45 times 10 to the negative 4. Now that's really small. 4.45 times 10 to the negative 4 is a really tiny y-intercept. We could almost neglect that. We could almost take it off. We're not going to, because we want to be accurate and really super duper precise. And it won't always be something we can get rid of, so we're not going to do that here. Now it wants us to solve, it says, calculate the molarity of a nickel chloride solution that has an absorbance of 0.512. Okay. So from here on out, that's what we're going to want to do. Okay. We're going to want to use that equation and plug in what we've got here. It's going to ask me here to calculate the molarity. Let's do that. Right? I'm going to take my equation there, I'm going to rearrange it so that I've got molarity by itself. You could also just go ahead and plug in the absorbance of 0.512 and then solve for molarity. Either way would be fine. In fact, if you'd like, we can do it that way here and work out the answer from there. Okay? So, tell you what, let's rearrange this equation for molarity by itself and then plug in the absorbance and see what our calculator gives us. All right? Let's rearrange that first. So to do that, to get molarity by itself, I first want to subtract 4.45 times 10 to the negative 4 from both sides. And then that would give me, let's see, absorbance. I'm going to abbreviate that ABS, minus 4.45 times 10 to the negative 4th. That would be on the left. And then on the right side of the equation, I would have 1.99 times 10 to the negative 3. Times the molarity, or concentration would be another word for that. Finally then, to get the molarity by itself, I want to divide both sides by 1.99 times 10 to the negative 3. And that'll leave it for me by itself. Now again, as always, I don't mean to insult your intelligence, so this is something you could do in your sleep. Then spectacular, that's great news. This will cancel out, and that would leave me with molarity on the right side. Okay. Hopefully that makes sense as far as just me rearranging the equation. I'm just going to clean that up and cancel those out and get rid of them. so that I've got a little tidier equation here, and then we can go to work and finish it, okay? So I'm just going to clean this up. Let's put molarity in here. That's all that's left on this side after that stuff cancels out. And now we can go ahead and solve. It says calculate the molarity if the absorbance is 0.512. So we're going to plug in 0.512 right there, all right? Let's go ahead and punch that in. 0.512 into my calculator. Let's get that slid in here. Should have had that ready. Sorry for the delay. 0.512 minus 4.45 times 10 to the negative fourth. We're going to get an answer there first, so hit enter. Otherwise, you got to use parentheses and deal with order of operations. So we're going to go ahead and hit enter, and then we're going to divide that by 1.99 times 10 to the negative 3. And that gives me a molarity here. It says of 257. Now remember, that's millimolarity. It was little m, big M. The concentration it's telling me is 257. Now if I go over here to my graph, or my data table, my absorbance here was about 0.512, which is very close to 0.5, which was one of the numbers we had. So the concentration, or the molarity, should be really close to the corresponding 250. And it is. It's 257. So the absorbance was just a little more than 0.5. The molarity was just a little more than 250. Makes sense. All I have to do is plug in the absorbance, solve for molarity, and off we go. All right. What does that really mean? 257 millimolarity. Millimolarity. That means there's 257 millimoles in every 1 liter of solution. Another way of saying that would be 0.257 moles, because millimoles are like millimeters. There's 1,000 millimoles in a mole. So this would be the equivalent of saying 0.257 moles, 257 millimoles. And on the bottom I have 1 liter. I could just as well say down there 1,000 milliliters, because 1 liter is equal to 1,000 milliliters. So all I've really done here is change the top from milli to regular moles, and the bottom from liters to milliliters. You could use either one of those top 2 numbers over either one of those bottom 2 numbers, and you'd have the same value as the original. All right, that's going to be helpful as we go to calculate our question here below. So we have in our solution 0.2 moles of nickel chloride. That's our solute here, and every 1,000 milliliters of the solution. And the question is then asking how many moles and grams of nickel would be found in 50 milliliters of such a solution. To solve that, we're going to start with 50 milliliters. And we're going to use this ratio that we've just established up here from the previous question as our first step in our conversion. So this is going to look just like the ones you did in the stoichiometry work in that beginning of the notes packet if you've watched that video, or in any milliliters to moles, volume to moles conversion from first year chemistry. Pretty old news how we do these conversions. I'm going to use the ratio that I've boxed there with my yellow highlighter, and I'm going to say that there are 0.257 moles of nickel chloride in every 1,000 milliliters of solution. And the reason, again, that I chose those is because I want moles. That's what it's asking me for right here. And I have milliliters. And I want those to cancel out. So in my calculator, the milliliters will cancel out in the units, and that'll leave me with moles. So let's punch it in and find it. 50 times 0.257 divided by 1,000. And that'll give me moles. 0.0129 moles of nickel chloride. Now, look at that. 0.0129 moles of nickel chloride would contain 0.0129 moles of nickel, because in every nickel chloride, there's 1 nickel. It would contain twice as many moles of chlorine, because there are 2 chlorines in every unit of nickel chloride, but this question isn't asking me that. This would also then be 0.0129 moles of the nickel, which is the part that we care about in this question, that nickel 2 ion that's in that compound. That's the first answer, how many moles of nickel. The second part of it, and the final calculation that we'll do here, is to convert that into grams. We need to go to our periodic table and say that 1 mole of nickel contains how many grams of nickel. All right. Zip over to your periodic table. Hopefully you've got one nearby. Find nickel here. Turns out I have a couple of them open apparently. And here's my nickel. 58.69 grams per mole. So bring that back over here. 58.69 grams of nickel for every mole of nickel. Now notice the 2 plus is there. That doesn't matter because 2 plus simply means, and hopefully you remember this from first year if you did it, 2 plus just means it's lost 2 electrons. And electrons are so small that their mass doesn't change the fact that it's still 58.69 grams. So we don't need to worry about that charge as far as the number from the periodic table. It still works. And I'm going to go ahead and cancel those moles out then, and that'll give me grams. So I'm going to take my last answer here, times 58.69 grams in a mole. I would have 0.754 grams of nickel. Because they called it the nickel ion, that's what we'll call it as well. So there are my 2 answers for that question. The moles. Oops, that's not the one I wanted. This one and this one. Moles and grams of the nickel ion. Now, it also wanted me to calculate molarity of the nickel chloride solution if the absorbance is 1.509. I'm not going to do that one with you, but what you're going to do is follow the same math that we used, okay, up above in the first calculation, but instead of an absorbance of 0.512, which we plugged in to that red equation, okay, we're going to plug in the absorbance that's given here in question 2. So we're going to use this equation again, but we're going to plug in an absorbance of 1.509. Now, for question 3 down below, we're going to go back and calculate absorbance. To do that, we're going to go ahead and use our original equation. That's this one up here. It's hiding out way up here at the beginning. The equation that we first got off of our best fit line graph. Okay. So absorbance, calculate the absorbance expected for a 0.375 molar nickel chloride solution. Absorbance, according to that equation up above, absorbance is 1.99 times 10 to the negative 3. Remember, that's the slope of our line. Times the molarity, so that's given here as 0.375. And actually, in our graph, we're going to need to treat that as 375 because this is given in millimolar. All the molarities that were in our data table were in millimolar. And so 0.375 is actually 375 millimolar. All right. If you don't quite understand that, just go with it for now, and we'll come back to it as we work out some of these together in class. And then the rest of the equation is plus 4.45 times 10 to the negative 4. So our absorbance is 1.99 times 10 to the negative 3. Punch this in. Times, oops, I got a goofy numbers there. Times 375. And then to that, we're going to add 4.45 times 10 to the negative 4. And that gives me then an absorbance of 0.747. And again, we could go to our data table and probably guess that would make a lot of sense. 375 is bigger than our biggest value. My biggest value was 316 up here in my original data. And that gave me an absorbance of only 0.63. If I used a solution that had a concentration of 375 millimolar, it would give me an even larger absorbance than that. And here it's predicting an absorbance of 0.747. One last question here isn't mathematical at all. It simply asks, why did you choose the color that you picked earlier? Remember, we picked red. We chose red because, as you remember, red is complementary to the green solution. Complementary, not as in saying nice things about it, but the opposite color, and so least like it. it's complementary to the green solution. So the red light will be effectively absorbed, or will be easily or effectively absorbed by the solution, and that's what we want. In the end, it gives us a more sensitive range. It allows us to measure absorbances with a greater sensitivity over a greater concentration. We'll get into that more in class again. There's an introduction here to just kind of how to use the simulator and how to generate an equation using your spreadsheet. I apologize for the length of this video, but there's a lot to tell you about as far as colorimetry goes, what that's all about, and then working through one of the examples as well. So there's kind of a lot going on here. The following problems really are just a matter of doing the same thing you just did, switching over to a different compound. So this next one goes to Cobalt Nitrate. You'll need to choose that, which it says here is a red solution. Start with a fresh spreadsheet. Set up your wavelengths with a color that's opposite of red. And then plug in the molarities that are given here from 40 to 300, collect absorbances, make a spreadsheet like you did with the last one, make a chart or a scatter plot graph, put in that best fit line, and then get the equation from the best fit line. And if you need to use this video as a guide for that, all the steps are done in order. You're going to do exactly the same steps, but with a different color of light and with different molarities, or in this case, millimolarities, that you're going to put into that simulator at Phet. All right. Now, the questions that follow, the calculations, very much parallel the ones that I just went through with you. So you do your best to see if you can't come up with that equation and then use it to calculate the things you're asked to find, like absorbance or molarity for a given solution. And then it'll give you a couple of those conversions to do with things like moles and grams of a particular component of the solution, like we had with nickel here. Right? Again, thanks for sticking it out, working so hard through this video. I appreciate your stick-to-itiveness and your effort with this. It'll pay off when we get into lab, and you're going to be a wicked genius before you even get there. Thanks again, and I'll see you in the next video.